Okay, welcome back. So continuing from where I left yesterday. So we were seeing the phase measurement using Lysage's pattern, and already we have seen one case where we apply two sine waves across the y plate and x plate. By y plate I mean the signal applied across the vertical deflection plate, and by x plate I mean the horizontal deflection plate. So we have two sinusoidal waveforms, same voltage, same frequency, and same phase. If that is the case, we get same phase in the sense, first of all, if we consider zero phase shift. Okay, that is same phase. That means I'll get a straight line with a positive slope, just like this. This is a positive slope. So this is a positive slope. So otherwise, if my two sine waves are having same voltage, same frequency, but if they are phase shifted by 180 degree, then I'll get a straight line, but that will be having a negative slope. Okay, that is a negative slope straight line like this. So that was the case we discussed last time, and yesterday we started with a case where the y plate voltage, y plate phase is 90 degree. Y plate signal is having a 90 degree phase shift with the x plate voltage. So this is the case. So just like yesterday's discussion, just extrapolate all the lines you just extrapolate, leave the numbers. Okay, now take the case here. So here there is no confusion because 0 and 4 are points at the same voltage and they are at a common point. Okay, so this is my common point, but this line is connected to this line which is having one more point in addition to 0 and 4. So 0 and 4 is already accommodated, so we have a confusion where to accommodate 2. So that confusion, if this waveform is not conclusive, or the placement of 2 is inconclusive here, you just go and see the next waveform. Here you can see that 2 is coming here and 2 that can be extrapolated here. So 0, 4 and 2 is accommodated in this line. So we are having 2 points. Now, like the case, we have 1 and 3 here. So there is some confusion here where to place 3 and 1. Can I place 1 here, or can I place 3 here, or can I place 3 or 1 here? So there is an ambiguity or confusion here. In that case, please go to the next waveform. Here you can see that 3 is here, so you place 3 here. 1 is here, you just place 1 here. So 1 and 3 is placed, that is placed along this line. Okay, so everything is covered. So that is how you have to draw the or match the points or mark the points. Now after you mark the points, you just complete. You can see that it's a circle. So what is the inference? If my voltage and frequency are the same, and if the waveforms are 90 degree out of phase with each other, then you can get a circle. Okay, so if it is 90 degree or 270 degree, 270 degree is equivalent to 90 degree. If for both the cases we get a circle. So to 90 degree and 270 degree we get a circle. 180 degree and 0 degree phase shift we get a straight line. Of course, for 0 degree we get a positive slope straight line, and for 180 degree we get a negative slope straight line. Okay, now we'll consider the next case where, suppose if the phase is something else, that is, if it is not 0 or 180 degree, or it is not 90 or 270 degree. So what is the case? So in that case, you can see that just extrapolate the lines. You can see that one does not have any confusion. That is, one is coming here. Also here also the one is coming here. I told the reference point. Please remember the reference point, the first point in the first quadrant. So here the reference point is this one. So this here it is the signal applied on the across the y plate is advanced by some phase. Okay, so one is here, one is also here. Okay, now we have 0 and 5, but 0 and 5, how do you place? So that is also again no problem, because 0 and 5 is coming at this line is intersecting here, and here also we have 0 and 5, that is also intersecting this plane, this line. So here also we have 0 and 5. Okay, no problem. Now here also you can place it 0. Okay, so this one also can be 0 and 5, because if you do that, this if you consider this portion also, then that column can be here. We can have 0 here, and here also we can have 5 here. So if you extend this one, we get a similar point here also, that can also be 0 and 5, but that is not marked here. Okay, then 2 and 4 is here. Now there is a confusion. Where should I place 4 and where should I place here? Should I place 4 here, or should I place 2 here or here? Or in that case, to avoid confusion, just go to the other waveform. You can see that 2 is here. So definitely this place is 2 and the other place should be 4. How to accommodate 4? 4 is also coming from here, and 3 does not have any confusion. 3 is here and 3 is also here. So join all the points. So here it is 1, here it is 0 and 5, here it is 4, here it is 3, and here also it is 0 and 5, here it is 2, and here it is 1 again. Join these times, these lines, these points, you get an ellipse. So for any other faces you get, so one there's a straight line, there's a circle, and in between for any face you get an ellipse. So that is the conclusion. Okay, so this is, so you can see that for this ellipse, the ellipse lies in the first quadrant and the third quadrant. So what is the inference? The inference is that, so I'll go to the next slide, this waveform. Okay, that is, here you can see that is if the major axis, so this is my major axis. So ellipse has a major axis and minor axis. So this is my major axis and this is my minor axis. Okay, and so this is my major axis. So you see the major axis. So if the major axis of the ellipse lies in the first and third quadrant, that is the slope is positive, as in this figure, the 21.3a, the phase angle is between 0 and 90 degree or between 270 to 360 degree. So from this figure itself you have to make a conclusion that if the ellipse is lying in the first and third quadrant, then phase may be between 0 or 90 degree or 0 to 90 degree or 270 to 360 degree. When the major axis of the ellipse lies in the second and fourth quadrant, that is when slope is negative, the phase angle is either between 90 and 180 degree or between 180 and 270. So from here itself you can make an inference. You will get an idea, that is, where is my phase, what is the phase difference between the two signals. Okay, now how do you calculate the phase correctly, appropriately? So before going into that equation, I just have to make some we have to make some conclusions here. That is, what is y1 here? What is y1 here? So y1 is the this ellipse will be making some intercept on the y-axis. So that height is y1. So what is y2? The full height, this much height is y2. So and likewise, what is x1? This ellipse will be making an intercept with the horizontal axis, that is x-axis. So this distance is x1, and this distance is the total distance, horizontal distance is x2. Likewise, this is for the ellipse with in second and fourth quadrant. Now what is the equation? So this is my equation. So this is how I calculate the equation. That is, the sine phi equals y1 by y2, that is equal to x1 by x2. We have already seen what is y1 by y2, y1 and y2, as well as x1 by a2. Anything you can take and then you can substitute and get sine phi. If you get sine phi, then okay, so we'll see the rest of the things. So we have seen the equation. Now we'll see some more things. That is, if what is the case? So you can see that a straight line becomes an ellipse. A straight line becomes an ellipse. Then the ellipse size increases, finally becomes a circle. So circle is happening for either 90 degree or 270 degree. Then this is a wrong thing. This should be the other side. This should be tilting to the other side. So this happens for angle greater than 120, greater than 90. Okay. So so this is if it is 150 or 210 degrees, and we get finally again a straight line which is for phi is equal to 180 degree. So this is in general what is happening, and we have calculated how, we have seen an equation how we calculate the phase shift. Now next thing is, how do you measure frequency with the Lysage's pattern? Suppose it's very easy. Suppose we have, this is the signal we apply across the x plates, and this is the signal we apply across the y plate. So you can see that the frequency of the signal we apply across the y plate is having twice the frequency of the signal that we apply across the x plate. So if we put the CRO in XY mode, this we'll see such a pattern, just a pattern like this. It resembles like 8. Okay, so definitely we know that the frequency here it is twice. So how do we calculate that? Okay, so we'll see some more cases. That is, suppose So this is the equation for that. Suppose for some signals, we apply some signal across the y plate and some signal with some frequency across the x plate, and we result such a pattern. We result in such a pattern. So this is the ratio, that is Fy by Fx, that is frequency of the y signal by frequency of the x signal, equal to number of times tangent touches top or bottom divided by number of times tangent touches either side. Okay, so see, that is number of horizontal tangents is also equal to number of horizontal tangency to number of vertical tangency. See, if I get such a pattern, I draw a horizontal tangent. So this horizontal tangent intersect at 2 points. So there are 2 intersections. So my numerator will be 2 horizontal tangencies, and I draw a vertical tangent. There is only one contact, or there is only one contact or one intersection. If you draw a vertical tangent here, there is again one tangency, one vertical tangency or one contact. So my denominator will be 1. That is why it is written as 2:1. Likewise, take the case. So here you can, if you draw horizontal tangents, you can see that there are 3 horizontal tangencies, that is 3 intersections. So, and if I draw the vertical tangency, then there is only one tangency, that is one intersection. If I draw vertical tangent here also, that is not going to make any change. So the ratio will be 3:1. Likewise, this is 4:1. Now, what about this case? Just to have an idea, that is, if we apply some signals with some frequency, if this is the pattern which results, and if I draw the horizontal tangent, there are 3 tangencies, 1, 2, and 3. And what about the vertical tangent? If I draw the vertical tangent here or here, there is one intersection here, there is another intersection here. So 2 vertical tangencies or 2 intersections. So this is ratio is 3:2. I hope it is clear. That is, we have such a pattern, draw the horizontal tangent, see how many intersections are there. So there are 2 intersections here, and either draw the vertical tangent here or here. You can see that there is only one intersection, that is 2:1. So numerator is 2 divided by 1. Okay, so Fy by Fx is equal to 2/1. Likewise, here also draw this, that is horizontal tangencies are 3 here, so 3 as the numerator, and vertical tangent either here or here. There is only one intersection, so the denominator is 1. So Fy by Fx is equal to 3/1. Likewise, Fy by Fx is equal to 4/1. Likewise, 3 intersections, so 3 as the numerator, and 2 intersections, therefore 2 is the tangencies, vertical tangencies, 2 intersections. So 3/2 equals to Fy by Fx. Okay, so this is how you get a relationship between Fx and Fy. Okay, now this case also will be, this is another case which usually find in Lissajous pattern. You apply some signal, you are not sure about the frequencies, you apply some signal and you get a display, a Lissajous pattern like this. Okay, you can see that there is a difference between this Lissajous pattern and this Lissajous pattern. Of course, all these Lissajous patterns are closed, all the lobes are closed, but here the Lissajous pattern is an open Lissajous pattern because one end is open. So such a Lissajous pattern is called an open-ended Lissajous pattern. Okay, so this can also result. So here we introduce a case called half tangencies. So this is the display we get on the CRO. So we simply draw the tangencies. Okay, there we consider the half tangency, that is, draw the horizontal tangent like the previous case, draw the vertical tangent like the previous case. So you can see that there are 3 intersections here. So 3 intersections, 2 are full tangencies. So this is full intersection, full tangency 1, second full tangency here. So 2 full tangencies and half tangency here, So the numerator will be 2 full tangency plus half tangency. So 2.5 is the numerator. And what about the denominator? Denominator will remain the same. That is, there is only one intersection, only one vertical tangency. So that means the denominator is 1. So my ratio is Fy by Fx is equal to 5/2. So this is how we simply, in a very simple case, we measure the frequency and go through the materials properly and read the cases for, that is for measurement of phase, get an idea. Okay, so if you vary the if we keep the strength constant, and if we keep the frequency constant, and if you vary the frequency, we get a pattern from straight line to